Hi everyone, and welcome to PyCon 2026. The upcoming session will be about demystifying the global interpreter lock by Bruce Eckel, and it's about if you were here the previous session, it was about removing the GIL, and now it will be about what you got with the GIL for free, and when you remove the GIL, so what happens and what you should be aware of when going forward in the next upcoming Python version. So let's welcome Bruce with a very warm welcome.
Yeah. Great. Thank you. Okay. All right. Okay. Sounds like I'm on. Gonna get my screen showing up. Is that possible? There we go. Okay. So this talk originated a couple of years ago when I was talking to Guido, and he casually mentioned something to the effect of he thought people were going to be surprised by some of the side effects that happened when the GIL is removed. And so that stuck in my mind, and I came up with a simple example, and I thought, okay, great, I can start with this example and expand on it. And it did get more complicated than that. And so if you, at the bottom there, you'll see the URL. Okay, so the GitHub repository has everything on it, including a book. So there is a book that tries to explain everything that I'm not able to explain here, and goes into more depth. So demystifying might be a little too ambitious. Let's hope that we can remove some of the mystery. Maybe a better thing to call it would be, we're going to look at the landscape before and after the GIL, when you take the GIL off. And this is the kind of thing we are promised. Notice it's dark and it's difficult, and everything has to happen in a line. And then over here on the right side, everything is beautiful threads, and it's going to be really easy and happy once we remove the GIL. So let's look at that. And I've facetiously named the first example, concurrency is easy. All of the examples and many more are in the repository, and there's a make file that will run them all. So in all these various different ways. So here's our project. Initially, we have this counter, and we want to count up as fast as we can. So we'll define a number of workers. And the workers will all work on the counter, this shared memory counter. They'll all work on it and try and increase the value as quickly as possible. So I have a function here, run in threads. Let's see what that does. So we pass the worker. We pass, well, I need to pass the value as, this is commonly called a thunk. It just means it's a function that takes no arguments, and it'll evaluate the value later. Otherwise, I would just get the initial value. I wouldn't see the result. And the number of threads. But the important thing here is this magic thing called the thread pool executor, which basically does a ton of work for you. It creates a pool of threads, and then you can submit your workers to the pool, and it manages them all, including something called structured concurrency, because normally when you fire a task off, you have to physically say, okay, wait until this is finished. You have to collect everything before you can move on. Structured concurrency does that for you. And so at the end, we will look at the value and how much time has elapsed. So let's have a look at that. All right, so all I have to do is say make. Concurrency is easy. Oh, actually, what we want to do with this one is I want to make it with the GIL. and we'll see what happens. Okay. All right, so we get 1,000,000. Doesn't take very long. Now let's try it without the GIL. So, all right. Okay, now the number is wrong. So that's a problem. Let's see if we can figure out what's going on there. All right. So the problem here is that counter plus equals 1 looks like a single statement, but it actually is translated into 4 Python opcodes. And if you're familiar with assembly language, opcodes are Python's equivalent of assembly language instructions. Basically, it's a way for us to take all these different ways of expressing code and reduce them to a number of simple expressions. And so what this is doing is it first loads the value of counter, it pushes the number that we want to increment it by, it performs this binary operation, which is plus equals, and then it stores it. Right. Well, that is a problem when we take away the global interpreter lock. And we'll go into that more as we go on. But the idea is that when we have a bunch of threads running, they can insert themselves at any point between opcodes. And so we could have 2 threads, we could have multiple threads that are loading the value of counter. Multiple threads can be incrementing this value, and then whoever the last one is to write that value back is the winner, and the others lose, and you get ultimately the wrong value. Before version 3.11, context switches, because that's what we're doing here. We're switching context every time we change from one thread to another. These could happen between any opcodes, but after 3.11, they made some changes so that counter plus equals 1 is actually atomic. But that's only when you're dealing with when the GIL is running. When we have 3 free threads, you've got all of your cores that are available, they're being utilized, and they're all running at exactly the same time. So they can step on each other, which is what we're seeing. So the solution to this is to use a lock. So we have this single global piece of storage counter, and a lock is a mechanism. It's also called a mutex. It's a mechanism that only allows one thread at a time to hold the lock. So what happens in our worker is when we're about to make our operation counter plus equals 1, whatever thread is doing it grabs the lock and holds it while it's doing the operation. And the with expression is what holds the lock, and then once it's done, it releases the lock. So only one thread of execution, only one task, basically, one of our workers is able to increment counter at a time. So what we've done is we've serialized access to this global variable counter using a single global lock for all the workers. All right, so let's see what happens with that. And let's see. And so let's clear it, and we'll say make camels no. All right, so we get 1,000,000, and we get 1,000,000. Okay, good. Only thing is the free threaded version. I should point out also that UV, you need to specify, especially if you install both versions, you need to specify whether using a GIL or free threading. And so you can see this is all taken care of by the make file. And if you just type make, it'll give you help for how to use this. So we're getting 1,000,000, but the free threaded version, the one that is supposed to magically make everything go faster, is actually taking a lot longer. So that's not what we really want out of this. So what's happening now? Well, we have all these threads that are trying to access this lock, trying to acquire this lock. So what we've got is contention. And that means they're all messing about trying to get a hold of this thing, and there's a whole bunch of CPU activity that's happening. And actually it gets worse because we're not just talking about what the operating system is doing, we're actually looking at it at the machine level, and the caches are being dumped, all kinds of messy stuff is happening. And you'll notice that I gave this example a kind of a weird name, the camel's nose, and that's because in places, there's a saying in places where there are camels in tents that once the camel's nose enters the tent, the rest of the camel will follow. And in this case, it's concurrency. And so you can't just go, oh, concurrency is simple, all I have to do is this little thing. You get the whole camel, which is what's happening at the operating system level, what's even happening at the machine level. How do you know when a task is complete when you're dealing with async I/O? There's a whole bunch of stuff. And you can't really answer a question unless you know the whole thing. And this is what makes concurrency so challenging, is that you kind of have to know everything. And you will sometimes hear people tell you, and if you express this, as I have many times, that this is actually way harder than you think, and I've had people say, oh, you're just not very smart. I know how it works. This is called the Dunning-Kruger effect. Many of you know this. The less you know, the more you think you know. And this is way the case with concurrency. So, so we have this contention, and that makes certain types of problems not run magically faster when you add, when you convert it to free threading. So what kinds of examples do work well? Well, the best is what we call embarrassingly parallel. And that means there is no shared anything. And this is an ideal case, but it happens in plenty of situations. So here's an example where all we're doing is some sort of calculation. I'm even throwing the calculation away, so who knows? Presumably we would want to return it at some point. But we're doing all these calculations, but they're completely independent of each other. So if I fork out a whole bunch of these things, none of them are going to step on each other. And notice I don't need a lock, so that's kind of nice. And if we, let's see. Oh, so what we're going to do is we're going to time the sequential version versus a threaded version. And when we do that, let's go back and okay, so we'll do that. And this one takes a little longer, but here it is with the GIL. It's taking longer than oh, there we go. Oh, yeah, so it takes a while. Now you notice this one, sequential, the threaded version sometimes actually takes a little longer, sometimes it's shorter, but in the second case, when we remove the GIL, oh, I mean, it's almost 7 times faster. All right, now we're seeing some results. This is promising. So the point is, there are situations, it's not magically going to make anything faster. There are some situations, however, that it does make faster. So here are some examples where free threading is useful, and you can run this test by saying make FT friendly. All right, so we just saw the embarrassingly parallel one. Another common example is when you're using async. So with async, you've got the event loop. You've got this one event loop that's running around looking at all of these IO requests, or all of these requests in general. So it's saying, are you ready, are you ready, are you ready? And it can deal with thousands of those. And the thing about the event loop is that when something is ready to be dealt with, you want to make sure that it happens very quickly, because otherwise your event loop gets tied up and it can't check all of the other things, and the whole point kind of goes out the window. So if you have something where it's going to take a while, you want to get it off of the event loop, and so we offload it onto a thread, and that tends to be a useful thing. And then there's several others, and all of these have examples which you can look at and see how they work. All right, so cool. There are situations, but the important thing to notice is that they are certain cases where it's helpful. Certain very useful cases, but it's not universal. Here's another thing, is that when you start using free threading, if you switch from the GIL version to the free-threaded version, there's going to be a cost. There's extra overhead. And this was one of the things that was a problem with earlier versions where they tried to remove the GIL, is that the overhead was so high that it was unacceptable. It was like, well, we're not going to fine everybody this cost in order for some people to use free threading. That's unacceptable. With the current version, which you can run this test by running make overhead. With the current version, well, it's averaging about, I don't know, 16%. You're going to get different results here depending on your machine and how you warm it up and clear out all the other things, et cetera, et cetera. But you'll notice there's a cost, and this is without taking advantage of any threads here. This is just the cost you're going to pay for your regular code when you remove the GIL, when you use the free threaded version. So that's something to know. You know, it's not all roses and sunshine. I think the best way to, at least currently, I think the best way to explain the GIL is the history of it. And so if we look at how Python got started, and I could, I'm putting words in your mouth here, okay, so when Guido got started with all this, he wanted to make something that was not a hard language to use, not like C where you had to deal with all these details. He wanted something for regular people to use without having to struggle with the computer science concepts. So he started out and said, well, one of the things that's difficult for people to deal with and causes trouble is memory management, having to alloc and free. I certainly didn't understand it until I had worked with programming for a while. And it's like, this is not something we want to deal with by hand. So let's have automatic garbage collection so we don't have to think about this. And so the simplest way to do this was reference counting. And that means when you create, when something needs an object created, that thing that is referencing the object, well, it makes a +1 on that object. And if somebody else looks at that object, if you pass it to a function or something, well, it adds another reference to it. So as long as there are things that need that object, it has a reference count of greater than 0. As they drop off, they go out of scope, they don't need it anymore, the reference count is decremented. And eventually, when it goes to 0, boom, you're ready to throw it away. You don't have to have a fancy garbage collector. What's interesting is that in the original version, so there's a thing called, that's not everything. There's also something that can happen called cycles. So you have an object, it points to another object, and then that object eventually points back to the original object. Might go through a big loop to do that. But you have a cycle. Well, in that case, somebody's always pointing, and so the reference count is greater than 1. So those things need to be dealt with, or in version 1 of Python, Well, the idea was, oh, we're just doing something simple. It's probably just going to be short stuff. It's not going to last long enough. This is just a simple scripting language, so it won't last enough. If there are cycles that take up extra memory, it's not a problem. The program's going to end soon enough and it'll all go away. Well, the language started getting a little more popular, and eventually that needed to be dealt with, but that didn't happen until version 2. Next, people were going, well, this is a great language. I like it as a glue language, but one of the things I'd like to do is be able to call C code. And so there needed to be some way to call chunks of C code, which could be very complicated and messy, but the Python programmer didn't have to think about that. All right, so the thing about that is if you're passing these Python objects to the C code and they're interacting with it, they have to maintain the reference count. So if they're using it or not using it, the reference count has to increment or decrement. And this became part of the application binary interface, and that is like how it is laid out in memory. And once that happened, that couldn't be changed because all the people who were writing C extensions were relying on that particular layout. And so if you decided to change that, it wouldn't work. So that put a limitation on how the reference counting could work. The next thing was, originally, Python was just saying, well, we're just doing what we've done in the past, batching things. You give me a file, I'll work on it, and I'll put out another file, things like that. Well, it turned out that eventually we had to do, well, hold that thought. I need to go over here and do this thing. All right, now I need to come back. So we needed to do that kind of thing, like, for example, for the keyboard. If you had a program running, you needed to have it check the keyboard periodically, various other kind of devices, I/O and stuff like that. We needed to pay attention to that. So this is a context switch. When I say hold that thought, going to do something, come back to it. That's a context switch. Now, it would be possible to build all that in, but the operating system already did that for you because it had threads. So Python just piggybacked on the operating system's threads, and so they look, there's a little bit on top of what the operating system does, but it's basically operating system threads. Well, a thread is basically a processor pretending that it is more than one processor, that it can do more than one thing. And so it's switching around, and you effectively have all of these things, even though back then and for quite a while, we did only have one processor, but all the threads made it look like you had multiple processors. So now these ref count updates could race with each other and cause trouble with reference counting. And because of the sequence of these decisions, we ended up with the most logical thing to do was, because all we're using the threads for at this point is to do the context switches. So we have a single interpreter-wide lock at this point. And the things that it protects is it's more than just reference counts. It's a whole bunch of other things. But in the end, you also get this kind of accidental thread safety. So even though you haven't written the code for concurrency, it works anyway, which is nice because for introductory programmers, they're not suddenly burdened with the idea of having to deal with threads. There's been a number of attempts to remove the threads, the global interpreter lock, and there have been attempts to work around the issues that is presented by it. And the attempts to remove it did not, they cost too much. They added too much overhead for single-threaded code. So that didn't work out. But then there are other things like multiprocessing. Well, multiprocessing means you have multiple operating system processes. So that means that they all have their own space, their own primary thread. They're completely isolated from each other. And they're basically controlled by the main Python, and they all have their own Pythons and their own GILs. Okay, this was pretty cool because it allows you to use multiple cores, but the problem is now communicating between those things involves a lot of information being transferred from one to another. So once again, a concurrency strategy solves a subset of problems, but we've never found one that solves all of the problems. So that's useful sometimes. Let's see, async IO. All right, that was cool. And if we had had that technology back at the beginning, maybe we could have skipped adding the GIL, who knows? Because it would handle the IO issue nicely. But that technology didn't really hit mainstream until the mid-2010s. So not available. Let's see, there's improvements to the interpreter. There's also, we're in the process still of, Eric Snow is still working on this, as far as I know, working on sub-interpreters, which is, it's all in a single operating system process, so the memory is visible to all of the things, but you have multiple sub-interpreters, each can run on their own core. So that shows some promise to solve, again, a certain subset of problems. And then finally, we've gotten this free threading version, which is still arguably experimental, but it appears to be cheap enough, and eventually maybe cheap enough to, who knows, it could become the mainstream one. The problem that we run into is that there are certain patterns that we're used to that are going to, that do break without the GIL. And so there's a bunch of things that you may be used to using that, because of their nature, the GIL is going to break them. And so one example is a registry, which involves a global dictionary that you add things to and remove and look things up from. If you have multiple threads doing this, then you can have them, they can stomp on each other. So after all that, should you even use concurrency? My argument would be absolutely not if you don't have to. If things run painfully slow, start by using Occam's razor, which is to say things like, what's the easiest solution that I can come up with that might work? Hey, faster hardware. Rather than programmer time, maybe you can just invest in faster machines. That might solve your problem. Profile and optimize, and your AI can help you a lot here. If you find a function with your profiler that is running slow, you could rewrite it in Rust. It's very easy, I've done it. You use the AI, it does amazing things, and you use this library called Pyo3. You end up with a module you just import, you don't even know that it's written in Rust, and suddenly things are running faster. One of the important things to remember is that there are a bunch of different types of concurrency problems. It's not a one solution fits all, and you have to understand the architecture of your system and what sort of concurrency problems you are encountering and the different strategies to solve them. Ending with an Escher image, I think is appropriate. And I also kind of like the fact that it says, it was supposed to say, even if your code works without the GIL, the libraries you call might not. And I like the fact that the U got kind of messed up because it suggests the idea of, oh, there was a race condition here that kind of screwed it up. So, all right, so I am out of time, but I have a little bit of time for questions, if there are any. I think, do we need to use a microphone for questions? Is that? Oh, sorry. There are microphones here if you have any questions. And the book covers a bunch more stuff that I was not able to cover in this short period of time. So, thank you. Yes.
Hello, thanks. I wanted to ask, I guess, so other languages maybe don't make this trade-off in terms of single-threaded performance. Is this just like the nature of interpreted languages? Is there a reason, or is this just the state of the world that Python is in, and now we have to consider it?
Well, I mean, this is these were a series of choices that were logical at the Gerald Weinberg has a great quote. It says, things are the way they are because they got that way one logical step at a time. And that's what we saw here. If Python was being designed now, it would be different. And this is a CPython thing. So if you look at Jython, for example, which I don't think is being maintained anymore. I'm pretty sure it's not. But Jython uses the garbage collector for Python. I think, what is that Japanese language? Somebody remind me. Ruby, okay. I think Ruby also ended up with the GIL. So but I don't think it's necessarily the nature of interpreted languages. I think it's just an artifact of how the sequence of decisions was made. And, you know, we might see, I'm sure we could see other implementations that might change things, but yeah.
Thank you.
Hi, really appreciated the historical context and just kind of going through, as you say, one logical step at a time. I have a somewhat banal question. You mentioned cache misses as an artifact of why that was so much slower. I think it was 100 times slower, which is like, whoa. But the cache miss is kind of, I can see the contention. Can you offer some insight on what specifically is being discarded, being thrown out of the CPU cache there?
Well, I did study hardware engineering when I was in grad school, but that was a long time ago, and they're much more sophisticated. And there's different kinds of caches. There's like a look-aside cache, and the problem is that basically it gets an image of what's going on, and it goes, all right, now I got this, and I can run really fast. And then you go, oh, except somebody else has changed the value of counter. And it goes, well, okay, I just have to dump everything and reload from the beginning. It doesn't have enough information to say, oh, just this one part changed, so I can leave everything else alone. And so when you have a cache miss, it just throws everything away, and then it has to reload everything, and that's complicated. And then you also have
part of that the fact that it's a thread, but it's inside of the Python interpreter. Is that part of like the interpreter state is taking up a lot of that space, and that's why you have to discard it?
Well, I mean, the CPU doesn't, it's not really aware of Python. All it's aware of is, oh, I've got this chain of assembly language instructions lined up, and are they legitimate or not? I don't promise to understand.
It's a complicated subject. Thank you.
Yes, yes.
Thank you for the talk. I appreciated the deep diagrams analyzing the performance across threading with and without the GIL. I was curious if you also went into looking at it with multiprocessing, specifically with the lens of like, we have a bunch of multiprocessing code already, how you decide if it makes sense to move to free threading or it's just not worth the trade-off. Can you speak to that?
Well, yes, I mean, awesome question, because that points out the art of all of this. It's and the fact that you have to know the whole camel to understand, oh, here's a situation where it might work. And then usually you have to try it out and then go, oh, wait, that didn't work for some reason. And then you can kind of dig in and go, oh, well, it's maybe we've got contention or cache misses, or the amount of information that I'm moving from one sub-process to another is too big, the cost. This is why it's tricky. This is why probably you'll have a job for a little bit longer than everybody else if you focus on this because of the trickiness. But the AIs are still pretty good at figuring a lot of this stuff out, and they'll just get better. So,
so do you think about things like if we have a lot of inter-process communication or a lot of like copy on write, things as good indicators then, or do you have like a set of things to look out for like, do we want to investigate the rest of the camel or just leave it as is?
Yes. Yes, all of that. I mean, this is why, I mean, I've tried to write a book on concurrency, and I get to a certain point and then I go, nope, I'm still not smart enough. And it's because I understand it a little better. It's because when you look at it, it's just, there's a whole bunch of strategies. And then over here, there's a whole bunch of problems, and you have to figure out which strategy or strategies to apply to these problems. And there's all these typically surprising things that will happen where you go, oh, I didn't expect that. And then you have to kind of figure out, well, what's going on here? Is there some way to adjust it? And like, this is why people have tried to come up with ways to make concurrency simple. And the only thing that I've seen that's been successful, I mean, async await has made it simpler, but the programmer still needs to, that's cooperative. And so the programmer needs to decide, where do we give up control? The only thing that I've seen that's actually been successful is pure functional programming, and then the run system can actually say, oh, I see you have something pure here, I can do that in parallel. So it can insert some parallelism. But as far as making it transparent or something that the programmer doesn't, I think only AI will be able to do that.
So I'm taking away from this is I have to do the migration to see if the migration was worth it.
Is the migration worth it?
Try going from multiprocessing to free threading to understand if going from multiprocessing to free threading was worth it. It sounds like I need to try it to understand if it was
Yeah, I mean, multiprocessing is still useful in some cases. That's the thing. It's one strategy, and the subinterpreters and async await, all these different strategies, they're still useful for certain problem domains. And you have to know, like, does this make sense? And so, yes, I guess I'd say my experience is that with AI, I'm able to try things out more easily, and so I'm not as afraid of the investment that's necessary to experiment. And so I guess that's what I would recommend mostly is go, oh, maybe this is better. Try it out, get your AI to help you generate the experiments and see if that helps.
Great, thank you.
All right, thank you. Okay, looks like everything. All right, thanks everybody for coming and listening.